Okay, so this is the continuation of the work that we did in previous section, or previous lecture, I should say. In the previous lecture, I mentioned about properties of rational functions. We talked about the theorem on horizontal asymptote for the graph of a rational function. Now, these are the steps that are recommended by the author of the book I'm using for graphing rational functions. So let's go quickly through the steps. Step 1, factor the numerator and denominator, find the domain of the rational function. So let me actually do this as we go through the example I have. So let's follow that recommendation, which is true. We always want factored form. That's why factoring is such a key skill in our work. So let's go x plus 3x minus 2. That will be the factor of the denominator. So we did the first part. Now we can determine the domain of the function. Remember, the domain of all rational function is always all real numbers, except what makes the denominator 0. So we have 2 and negative 3. Each of those will make one of the factors 0. Negative 3 makes this 0, 2 makes the one next to it 0. Okay, so we have that one. That would be the domain. Now, that's step 1. We just did the step 1. Check. Step 2, write R in lowest terms. Well, R, remember, R is the rational function in lowest terms. At this step, that means if there are common factors, you cross out common factors from top and the bottom. I don't see any common factors here, so step 2 is done. There are no common factors. The expression is in lowest form or simplest form. Step 3, find and plot intercepts of the graph. Use multiplicity to determine the behavior of the graph of R at each intercept. Okay, so let's find the x, y intercepts. First of all, the y-intercept, and that's when evaluate R, the rational function, at 0. That's when x is 0. So that's going to be 0 squared divided by 0 squared plus 0 minus 6. 0 divided by negative 6 is 0. Okay, so we have 0, 0 as the y-intercept. So anytime y is 0, x will naturally be 0 also, because we plug in 0 for x. So this means the graph runs through the origin. Now, okay, so that's what that means. Okay, and then what else do we need? Well, let's take a look at the x-intercepts. For the x-intercept of a rational function, we set the numerator of the rational function equal to 0. That means x squared equals 0, and that means x is 0. Okay, so our x-intercept is going to be at 0. That's the only x-intercept. Now, the multiplicity of this intercept is 2, remember, because we have x squared. The multiplicity is 2, and that means at 0 the graph will touch and bounce at 0 because of even multiplicity. This goes back to, again, the lecture we had on graphing polynomial function. This is 2 lectures back. Perfect. So we'll keep that in mind. And that's what it meant, determine the behavior at each intercept. The behavior here was touch and bounce behavior. Step 4, find vertical asymptotes. Graph each vertical asymptote using dashed line. Determine the behavior on either side of the vertical asymptote. Okay, we'll do that. Step 4, the vertical asymptotes. So vertical asymptote, those are places where denominator is 0, right? Denominator equals 0, and we already decided those are the values that cannot be in the domain, and they become the vertical asymptote. So x equal 2, x equal negative 3. Then I'll transform all of this information onto a graph in a few minutes here. Next step, find horizontal or oblique asymptote. Remember, we cannot have both. Most of the problems I do will be horizontal asymptote because that's what you will do in your future courses most likely. Graph asymptote using dashed lines. Find points, if any, where the graph intersects the asymptotes. Plot the points. Remember this part where the graph intersects asymptotes. The graph of a function may cross its horizontal or oblique, and it's going to be one or the other. My focus is on the horizontal. So the graph may cross its horizontal asymptote. We need to determine those. So for the horizontal asymptote, we're going to cite the theorem on horizontal asymptotes. The degree of numerator n is 2. The degree of denominator m is 2. See, 2 and 2. Numerator n, denominator m. Because n is equal to m, therefore the ratio of coefficients a sub m over, and I use n, sorry, for a sub n over b sub m is the horizontal asymptote. Now, for this example, a sub n is 1, b sub m is 1 also. Therefore, the equation for the horizontal asymptote is going to be 1 over 1, or simply 1. All right, so we have that one. Y is equal to 1. And again, all this information will be transformed to a graph momentarily. Let's see what else. So we did that. Oh, will the graph cross the horizontal? Question. Will r of x cross its HA? Remember, the horizontal may be crossed, but vertical will never be crossed. So we're going to set the y for r equal to the y for the horizontal asymptote and see where it's going to take us. The y of the rational function is the function itself. So it's going to be x squared over x. That's x squared over x squared plus x minus 6. Set it equal to the y of the horizontal asymptote. All right, and then we're going to cross multiply, give this a denominator of 1 and cross them. Okay, when we do that, we're going to get x squared equals x squared plus x minus 6. All right, subtract x squared from both sides. We get x minus 6 is 0, and we actually have x equals 6. Okay, so wow, interesting. So the answer, will the graph cross the horizontal asymptote, is yes. Where? At x equals 6. The value of the function at that point, r at 6, is going to be 6 squared over 6 squared plus 6 minus 6. And that is 1. See, no surprise, the y is going to be 1. This is additional step. We didn't really need to do that because we have the y for horizontal asymptote. The point where the graph will cross the horizontal asymptote is at 6, 1. All right. And I think that's about all. We've reached this point. Use real zeros of numerator denominator to divide the x-axis into intervals. Determine, I'm reading number 6. And determine where the graph of r is above, below the x-axis, choosing a number in an interval. So at this point, you just plot points. You see that? You just plot several points, and just to affirm whether the graph is above or below the asymptotes or the x-axis. Use the result in 1 through 6 to graph the function. All right, so let's do all the results that would be from right about here down. Okay, so I'm going to bring my coordinate system first, and then we're going to graph this. Okay, let's transform the information. First, the y-intercept was at 0, 0. So the origin is actually the intercept here. Okay, let me not do that. Let me put the 0 here. Okay, so that's the y-intercept. The x-intercept was at 0, multiplicity of 2, so it's going to touch and bounce. And at this point, there, multiplicity of 2, and x squared is a parabola, remember? The power functions we talked about, x squared, x4, x6, and so on. X squared, it will touch and bounce like this. X to the 4th will be flatter. X to the 6th will be much flatter than the other two. So it's just going to be touching and bouncing like a basic parabola does. Now, it can either do, parabola can open up or downward, right? So the question is which of these two. So we're going to put that on hold for now. The author recommends when we plot points, but I can actually do without plotting points. See how this is going to turn out. And then we're going to graph the vertical asymptotes, right? Now the vertical asymptotes, we found them here. We just did the horizontal asymptote. The vertical asymptotes are at 2 and -3. Okay, so let's say this is going to be there. I'm gonna do x equal to 2. Suppose this is x equal to 2. All right, vertical asymptote x2, x equal -3. That one, I'm going to make it go over here. So that's x equals -3. All right. Now, because these are the vertical asymptotes of the graph must approach them, right, from one or the other side as we approach 2 and -3 from the right and left. The horizontal asymptote, remember, is line y equal 1. We had that up here also, right in here. The horizontal asymptote was line equal to 1. What else? And the graph's going to cross this horizontal at 6, 1. At 6, 1. So that means I need to stretch this a bit further at 6, 1. So call this 6, and 1 would be here. The horizontal asymptote is at y equals 1. That means the graph has to approach it as x becomes very large or very small. And there you go. So these are all the, I would say, possibilities with the arrows. This is all the ways that the graph could approach the horizontal vertical asymptotes. So now let's go through and see if we can eliminate these. The fact that there's only one x-intercept, remember, is this one at 0. One x-intercept suggests that, for instance, this graph cannot do anything like this because it will create another x-intercept here. All right. Now the question is, will it go up like this or will it go down like this? And the answer is going to be going down, because if it goes up, notice it creates additional points that it has to cross the horizontal asymptote. And we only, remember, we just found out there's only one point where the graph crosses this horizontal asymptote. Therefore, this is ruled out. All of these are ruled out. There you go. And the only acceptable possibility here is for the function to do this, right? It has to come and approach x equal -3 from the left, and it has to approach it from the right. There you go. Again, these graphs are not going to be perfect as long as they are realistic depiction of what's going on. That's good enough for our work. We can always use graphing utilities to graph these more accurately, right? So there you go. That's that part of it. Now the other question is this: is it possible for the graph to do? It has to cross or touch this point, right? Can it do this? Well, the answer is no. It cannot come from below because it will create an x-intercept. So this is ruled out. And the other question is, well, can it do something like this? Or is it going to go like so? Well, for this one, It can be either or. So we just need to plot a point and see whether we are above or below the line y equal 1. And for this one, it will actually do something like this, because there you go, that's that part of it. It will cross it, and then it will go back and approach y equal 1. Okay, and it's not going to do something like this. Okay, and on the left side, to the left for this segment, again, this is not going to be a choice because that will create an x-intercept. So this part is out. The only feasible possibility would be to do something like this, to where it will approach both asymptotes. Again, for extreme values, you see how the graph is approaching it, and that will be the graph of this function, right? And if you want, you can also plot points again. So for instance, let's do r at 7, and you can see r at 7, we're going to get a number that's going to be less than 1. And here it is, 7 squared over 7 squared plus 7 minus 6. The numerator is 49, the denominator is 50. You see that? We are just shy. 49 over 50 is 0.98. So that's just shy right in here. We're just shy of 1. So this would be, that's how I know it's going to dip below. And then by virtue of horizontal asymptote, it has to come back up and approach that line. Okay, so we're done with this example. Let's do a couple of more examples, and that'll be it for this section. In my next example, let's say we're going to do the same things we did earlier, all those steps. I may not go in order of the steps that I displayed, but we will eventually cover all of those. So anytime we're given a rational function, again, we need to, if it's not already in factored form, we have to factor this. In the factored form, difference of two squares. Notice we used this special factoring skill quite a bit. That would be x squared minus 4 and x squared plus 4, and we can further write this as x minus 1 times x plus 1. That's the numerator. The denominator, difference of two squares, again, x squared minus 4 is x minus 2, x plus 2, and x squared plus 4. So that's like a step 1. Make sure the rational function is in lowest terms. Now, once we have that, let's determine our domain. Domain is all x, so that x cannot be 2 or negative 2. Note again, x squared plus 4 will never be 0. So it doesn't matter what you put in, you square plus 4. There's no way that can be 0. That would be the domain. Anything but 2 and negative 2. From the values that we exclude from the domain, we can get the vertical asymptotes. The equation of those would be x equals 2 and x equals negative 2. Right? From the theorem on horizontal asymptotes, the degree of the numerator, that's n, is 2. It's a second degree polynomial. The degree of denominator is 4. It's the fourth degree polynomial in the denominator. Okay, and because numerator is less than denominator, so the x-axis would be the horizontal asymptote. X-axis, or line y equals 0, is the horizontal asymptote for the graph of the function. So we have that part. What else? So let's do our x-y intercept. For x-intercept, we said the numerator equal to 0. And these will also give us the zeros of the function. So the numerator, that's x plus 1, x minus 1 equal to 0. And we get x is negative 1 and x is 1. So we have those two x-intercepts. Now, what else do we need? We got the vertical asymptote, horizontal asymptote, x-intercept. How about y-intercept? For y-intercept, we're going to do h at 0. Evaluate the function at 0. Let me move down here so I have more space. H at 0, and you can actually go to the original, will be easier, right? Rather than factored form. 0 to the 4th minus 16, so it's going to be 116. That means positive and just barely above 0. Very close to 0. 0 and 1/16. Wow, interesting. Okay, what else? We got the x-intercept, we got the y-intercept, and Wall the graph. We always have to answer, if there's a horizontal asymptote, we have to answer this question. Will h of x cross its horizontal asymptote? And to answer the question, we're going to set the y of the function equal to the y for the horizontal asymptote. And the y of horizontal asymptote is 0, correct? And let's do that. So that would be x squared minus 1 over x to the 4th minus 16 equal to 0. And again, you can cross multiply, or from this we get x squared minus 1 equals 0, because again, a fraction, a rational function is 0 only when the numerator is 0. So from this we get a couple of intercepts. Yes, at 2 points it will cross the horizontal asymptote, and remember, the horizontal asymptote of this one was the x-axis. Okay, so that will suggest the graph will cross the x-axis at 2 points. Now the multiplicity here is going to be 1, so it's going to go right through this, right? It's not going to touch and bounce. In fact, remember we talked about zeros. The zeros are x equal 1 and x equal -1. The x-intercepts are the zeros. All right, I think we're good. So let's go and put all of this together in the form of a graph now. Okay, so here I have my coordinate system. Let's begin with the horizontal asymptote is going to be y equals 0, x-intercepts 1, -1. So let's say here is 1 and there's -1. Those are the x-intercepts, 1 and -1. The horizontal asymptote was y equals 0, or the x-axis, correct? Right up here. That's the horizontal asymptote. The y-intercept, 0, 116, just barely above 0. So I'm just going to have to kind of make it a little bit more visible by going up a little higher. Okay. Now, we did mention the horizontal asymptote is like so, and the graph will cross it. It will cross it at 1 and -1. This is 0 and 1/16. And then the vertical asymptotes were at x equals to 2. That's this one. And x equals -2 would be this one. X equals -2. Right? And the graph must approach the vertical asymptote in a number of ways. We'll go through elimination to eliminate some of these possibilities. Okay, and there we have it. Now this function, by the way, we haven't talked about many of these in this section or prior sections, but this function is an even function. It is an even function because when you do h of -x over -x to the 4th minus 16, you get the original function back. Right? So that's going to be the original function. That means the function is symmetric with respect to the y-axis. And now we can actually graph this thing. So this is the y-intercept. Again, the function has to go through here, and it will go and approach the vertical line this way. And again, by virtue of symmetry, it will do the same thing on this side. Okay, so the two sides must be symmetric. I guess my 1 isn't quite 1 here. That's why it's going to be a little bit more to the right. There you go. Because these are supposed to be equidistant. There. So now that's more of a symmetry. That's that part of it. And you can actually plug in a number just to make sure. How do I know it goes here, not up here? Well, now here's the thing. If it goes up, suppose it's going to go up. I'm going to make it go up. If it does this, well, how's that going to go? See, that's just not gonna work the way it is. And you can also plot a few points and see to either side of 1, pick a point here or here to see that the function will be below the x-axis. All right. Now, for the other portion, again, we do have these horizontal asymptote. The graph can either do this, or this one, or this one. And for this part, I just picked a value. So for instance, if I do h at 3, okay, that's over here. H at 3, let's see, h at 3, it's going to be 3 squared minus 1 over 3 to the 4th minus 16. 3 squared minus 1 is 8, and 3 to the 4th minus 16, that's 81 minus 16, and that's 65. Now, forget the 8/65ths as a number. It is positive, right? If it's positive, means the function is above the x-axis. So this part is ruled out. And therefore, we're going to go with this portion of the graph looking like so. All right. And there you have that one. And what else? The other side, same thing. You can pick a number that is less than -2. But remember, the graph is symmetric. We said the function is even. So once you have one branch, reflect it to get the other one. So we don't need to actually plot points for that one. And I'm just going to graph it. It's going to go like this using symmetry. And that'll be the graph of this function. All right. So actually the graph of polynomial functions, I really like them. They're not boring, right? They're actually a little exciting, a little interesting on how they behave. Okay, and let's take a look at the last one. We'll finish it with this example. Suppose my polynomial function now, r of x, is x squared plus x minus 12 divided by x squared minus x minus 6. So we always factor these rational functions. We factor the polynomials on top and polynomial on the bottom. So the factored form of the numerator, that's going to be the top. In the denominator, we're going to go x, two numbers multiplied to -6. Let's go -3 and 2. The sum would be -1. And notice there is a common factor here. The domain of this function, before we remove anything, domain is all x such that x may not be 3 or -2. We look at the domain before we simplify the expression. And then, if there are common factors, we remove them. The points that were removed at x equal to 3, therefore, I'm going to say at x equal 3, there's going to be a hole in the graph, because that's actually not part of the domain. Okay, so at x equals 3, there's going to be a hole in the graph. All right, and then we can go through some of the other stuff that we went early on. That's the domain. So the horizontal asymptote, degree of numerator n is 2 equals degree of the denominator. Therefore, the ratio of the leading coefficients, y equal 1 over 1 equal 1. That's going to be the horizontal asymptote. Okay, is the HA, horizontal asymptote of the graph of the function. And what else? We have the horizontal asymptote. We got the vertical asymptote. Place where denominator cannot be 0 in reduced form, which is x plus 4 over x plus 2. Remember, we already dealt with x equal 3. That's just going to be the hole in the graph, not a vertical asymptote, but a hole. The vertical asymptote is going to be x plus 2 equals 0 or x equal negative 2. This graph has one vertical asymptote. Let's do our y-intercept. The y-intercept, we do r at 0. And we're looking at, again, the reduced version. 0 plus 4 over 0 plus 2, which is 2. When x is 0, y is 2. There is our y-intercept. X-intercept. Well, the x-intercept, that's when the Rx is 0, and for a rational function we set the numerator equal to 0 only. The numerator is x plus 4 right up here again. We're going to set the numerator of the reduced version equal to 0. So from this we get x is equal to negative 4. The intercept is at negative 4 comma 0. All right, I think we are good. Oh, one last question. Will the graph of r of x cross its horizontal asymptote? If there is a horizontal asymptote or slant, and my focus is on horizontal, we always have to check this. So we look at the reduced version of the function x plus 4 over x plus 2, set it equal to the equation of horizontal, right? Which is 1. In other words, I'm doing y for the function equal y of the horizontal asymptote. And what we're saying is this. Let's say here's the function, here's the horizontal asymptote. At the point of intersection, if there is one, the point of intersection, this point will be on both, on the horizontal asymptote and on the graph of the function, right? So the xy must be the same. That's why we set the y's equal to each other. Now, let's solve this equation. Cross multiply, we get x plus 4 equal x plus 2. And the x's subtract from both sides, and we're going to get 4 equals 2, not. The answer is going to be no. Remember, the graph is not going to cross the horizontal asymptote. So now let me bring my coordinate system, and then we will graph it and finish it up. And here it is. So let's take a look at our key points again. Horizontal asymptote is at y equal 1. So let's say this is y equal 1. The horizontal asymptote. And the graph is not going to cross the horizontal asymptote, it's going to approach it. Perfect. The vertical asymptote was at x equals negative 2. So we need to graph this one. X equal negative 2 would be, let's say, here. This is x equals negative 2. And again, the graph has to approach these asymptotes. In the case of horizontal, for extreme values of x. In the case of vertical, as x approaches, in this case, a negative 2. And there you go. Okay, and here's my negative 2. Let's see, the y-intercept was at 0, 2, correct? Y-intercept was at 0, 2. And so let's say that's where this one is. Y-intercept as 0, 2. And remember, the graph cannot cross the horizontal asymptote, so it's not going to do anything like this, right? And the only thing it can do is to go through and approach. So that's how it's going to look like. Now let me just smooth over it, make it look a little better. And there you have it. That's this part. And then on the other side, let's see, because it's going up in that direction, therefore this is not an option, because notice it will create an x-intercept. And we said that there is no x-intercept, right? X-intercept, oh, there is one, but it's at -4, sorry. X-intercept is at -4. But still, this way, that's not -4. It will create an additional x-intercept. So that's ruled out. -4 is here. When x is -4, we found x-intercepts. So that's y0. There you have it, at -4. And again, this part is ruled out because it will miss the x-intercept. It cannot go like that because you cross the horizontal asymptote. So these are all ruled out. Isn't that cool? We just go through this elimination process. And we simply graph this function now. And let's see. That's that part of it, and here's the other side of that. There. Go through this one. Not too bad. So we were able to graph this rational function. All right. And there you have it. So we've done enough examples, I think, between this lecture and the previous lecture. Although previous lecture didn't do any graphs, but more of the properties or characteristics. So we just didn't do the graphs, but we did everything we did in this section. So let me cut the video short here to make up for the longer videos. Thank you for watching, and we will continue this discussion into our next lecture, where we talk about polynomial and rational inequalities. Again, thank you for watching, everyone.